So far, we had reviewed the basics of TrustZone for ARMv8M. The following will focus on the TrustZone implementation on M2351. The M2351 is Nuvoton's first microcontroller which supports TrustZone. It's based on a Cortex M23 processor and has maximum clock rate of 64 MHz. The internal memory includes 512 KB flash and 96 KB SRAM. A number of master peripherals are attached to AHB5 bus, and the other slave peripherals are attached to APB bus. On this M2351 block diagram, you can see some hardware control units that are colored with dark yellow. These control units are used to support TrustZone. I'll discuss these control units one by one in following slides. The first one is the Implementation Defined Attribution Unit, and its abbreviation is IDAU. The IDAU is non-programmable. It defines the default secure and non-secure partitioning of address space after power on or reset. The IDAU uses address bit 28 for the partitioning. The bit 28 of a secure address is 0, and bit 28 of a non-secure address is 1. For Cortex M processor, the address space is divided into 8 memory regions, include code, SRAM, device, and so on. According to the bit 28, each memory region is divided into 2 subregions. One is secure and the other is non-secure. In order to store entry points of secure APIs, the lower half of code and SRAM regions are defined as NSC. But the first 2 KB of secure code region is defined as secure to avoid fake SG instruction remain in flash area after power on. The abbreviation of Security Attribution Unit is SAU, and it's also used for address partitioning. The SAU is programmable, and it can be used to override the memory security state defined by IDAU. In M2351, up to 8 memory regions can be defined by programming SAU control registers. The SAU CTRL control register contains the enable bit of SAU. To set up a SAU memory region, firstly, write the region number into RNR register, then write the base address and end address into RBAR and RLAR registers. And the memory region defined by SAU is either NS or NSC. The NSC bit in RLAR register denotes the memory attribute. If NSC bit is 0, the SAU region is non-secure. If NSC bit is 1, the SAU region is non-secure callable. When SAU is enabled, those memory addresses not defined in SAU regions are all secure. Both IDAU and SAU are used for address space partitioning. For a given address, its security state is decided by comparing the IDAU and SAU definition. The higher security attribute is selected for the given memory address. The priority sequence of security attributes is S, followed by NSC, and finally the non-secure. Therefore, the SAU can change the security attribute of a memory region from NS to S, or NSC to S, but cannot change the security attribute in reverse direction. The address partition is completed by IDAU and SAU together. After that, the processor knows which memory areas are secure and which areas are non-secure. For the M2351, all the memory and peripherals are secure after power on or reset. A secure address range is allocated for each hardware resource, but if a hardware resource can be changed to be non-secure, a non-secure address range is also allocated for it. These two address ranges have the same address value except for bit 28. If a hardware resource is assigned to be non-secure, it will only respond to an access to its non-secure address range. The security attribute of flash is configured by FMC, which stands for Flash Memory Controller, and the security attribute of SRAM and peripherals is configured by SCU, which stands for Security Configuration Unit. In the M2351, the flash areas include LD-ROM, AP-ROM, and user configuration words. Only the AP-ROM can be changed to be non-secure. The others are always secure. There is a register NSCBA in FMC. It is used to define the starting address of non-secure region in AP-ROM. Its length is 24-bit. Once NSCBA is programmed, the AP-ROM is divided into a secure and a non-secure region. The secure region starts from offset 0, and the end address is the NSCBA's value -1. The starting address of non-secure region is the NSCBA's value, and extends to the end of AP-ROM. Suppose that AP-ROM is divided into secure and non-secure regions. A processor in secure state can access the secure AP-ROM through a secure address, and access non-secure AP-ROM through non-secure address. A processor in non-secure state can only use a non-secure address to access non-secure AP-ROM. The other accesses are unsecure and will be blocked by FMC. The unsecure accesses include three cases. First, a secure processor uses a secure address to access non-secure AP-ROM. Second, a secure processor uses a non-secure address to access secure AP-ROM. Third, a non-secure processor uses a non-secure address to access secure AP-ROM. The SCU contains a set of control registers to configure the security attributes of SRAM and peripherals. The SRAM is divided into 12 blocks. Each block can be set as secure or non-secure individually. Similarly, each peripheral can be configured as secure or non-secure. For example, there are 3 UARTs in M2351, which are UART0, UART1, and UART2. Each UART can be configured as secure or non-secure individually. If a peripheral is secure, that means all its control registers of this peripheral are secure. In M2351, some critical peripherals cannot be configured as non-secure, such as FMC, clock controller, crypto accelerator, WDT, and so on. After the configuration is done, SCU will monitor the bus transactions. Suppose that a processor or master peripheral is secure. It can use secure address to access a secure SRAM or peripheral, and use non-secure address to access a non-secure SRAM or peripheral. For a non-secure processor or master peripheral, it can only access non-secure SRAM or peripheral through non-secure address. The other accesses are unsecure and will be blocked. There are 4 unsecure access cases. First, a secure processor or master peripheral uses a secure address to access a non-secure SRAM or peripheral. Second, a secure processor or master peripheral uses a non-secure address to access a secure SRAM or peripheral. Third, a non-secure processor or master peripheral uses a non-secure address to access a secure SRAM or peripheral. Fourth, a non-secure master peripheral tries to use a secure address. After power on or reset, entire SRAM memory is in secure state. The initialization code can program register SRAM NSSet to set the SRAM block to be non-secure. The length of register SRAM NS set is 12 bit. Bit N controls the security attribute of SRAM block N. For example, bit 0 controls block 0, bit 1 controls block 1, and so on. 0 indicates that the corresponding SRAM block is secure, and 1 indicates non-secure. All peripherals are in secure state after power on or reset. The initialization code can program a set of control registers to change some peripherals to be non-secure. These control registers include PNS set 0 to PNS set 6 and IONS set. Each bit in PNS set X register controls the security attribute of corresponding peripheral, where 0 for secure and 1 for non-secure. The GPIO ports are configured by register IONS set. Bit 0 controls port A, bit 1 controls port B, and so on. Similarly, 0 indicates secure state, and 1 indicates non-secure state.